Good evening, everyone. Welcome to this session on data science. I think I need to, okay, recording is started. So before we get started into our today's session, if anyone has any queries on the previous sessions, we'll first spend some time to get them addressed. Then we'll move on to our today's session. All right, then possibly you can keep posting your question. Okay, hashing in short. All right. It's a very simple concept. Hashing reduces the number of categories. Right? Probably based on some business logic or based on the frequency, you are combining various categories. So just simply calling it as others or something like that. So because of that, what could very well happen is when you are after doing the hashing, when you go for one hot encoding after hashing, obviously the number of columns that are getting created, number of additional variables that are getting created, additional features that are getting created is getting reduced, and which means the complexity of the model is directly getting reduced. So that's one of the reasons. Probably we can look at all these aspects as well as we move. So what I am planning is today I will talk about feature selection mechanisms, right? And from tomorrow onwards, I'm still working on it. But from tomorrow onwards, I'm planning to take up an end-to-end case study. Right? So the same loan example that we have started off, I wanted to build an end-to-end case study. So looking at that loan data, doing all the activities in a step-by-step manner. Right? So if at all this loan data is given to us, now what all can I do on the top of it? Right from whatever the various aspects that we have discussed till now, I plan to put that in a kind of a serial sequence kind of thing, so that what you can very well do is when you are taking up that, when you are trying to work on any other data set, especially I want to take one case study for classification problems, because once we are done with this feature selection, we are more or less ready to get into the various algorithms. So I will take up one case study for classification. I will take up one case study for regression problem. And I will probably take up one case study for clustering. Right, which is what will take us through the end-to-end implementation, right from all the aspects that we have. I'm trying to put in almost all the aspects into each of these case studies. So sometimes some things that we have discussed in detail, probably we will move much faster, and probably we will spend time on discussing what is happening behind the algorithms. I may not get into too much of mathematics for each of the algorithm, but functionally, I will talk about what is happening with each of these algorithms. Right. So that is what would be the plan. So we will use hashing also as one of those use cases, right? So that you can clearly understand when we are doing the data clarity, we can very well do this kind of a hashing and one hot encoding. We'll try out all the various aspects that we have discussed, right? And that master notebook, which I would be sharing with you, will contain the end-to-end process for classification. The whole thing in one single notebook. Probably it's from a practitioner's perspective, right? So possibly by tomorrow evening, I'll try to work out on the entire coding, or at least in phases, I will try to work on it. So that probably that is one way you can understand how you can compare various algorithms. So we can very well look at all those dimensions as such. All right. Yeah. Any other questions from anyone else? All right. So what I suggest is you should also parallelly take up some data sets. I don't know whether you are getting sufficient time or not, but that is the way you learn, because once this sessions are over, it is very much possible that you would also start ignoring this, right? Which means probably this is the time where you may have to spend some time. So you should have taken some other data set parallelly. So if you want, I'll share 2 or 3 data sets, right? What you should very well try to do is probably whatever I have done, either try to replicate it on that data set by using the code, because I'm sharing the code, whatever I'm working on. Either reuse that code or try to write it in a better way also sometimes. So some kind of cleaning activities, some kind of outlier handling activities, etc. You may want to do it better than what I might have done. So doing all those things would give you more confidence, right? I suggest that you should start doing all those activities. Take up some other data set from Kaggle in the area of your interest. Try to work on it. All right. Okay. So let me just get on to our today's session. So today I'm going to talk about today I'm going to talk about feature selection. We have talked about many data pre-processing activities, feature extraction, feature engineering, data cleaning, pre-processing, one hot and handling the categorical variable, handling the outliers, handling the missing values. There are a lot of things that we have discussed. We will try to incorporate all of them into one single case study, right? Today, I just want to talk about a few more things, because these are all the pre-processing activities before we actually jump into building of the models, right? So once I do this, I thought on one single data, if I do all these activities one by one, slightly on a faster mode, and be ready with the model building activity, so that we will talk about different models and then execute, because once we execute, we may have to compare. So the process behind doing that activity. All right. So today I'm going to talk about feature selection. Feature selection is nothing but shortlisting of some of the features, eliminating some of the features, retaining some of the features. So basically that is more important for us, because too many features in the model is going to eat up both the time and the memory. So all the computing resources are going to become more strenuous. Unless that variable or a feature is an important feature in the prediction process, there is no point in having that feature in the model. So that is what we are looking at when we are talking of feature selection. So importance of feature selection, why to use feature selection. Then we talk about types of feature selection, both univariate and multivariate. So univariate, we talk about the remove. So basically, multivariate, we will. It's like multivariate outliers and all those things. But in the univariate category, you would typically be looking at removing the features with low variance and highly correlated kind of features you would like to remove. So we have two different kinds of methods, broad methods that come under feature selection. One is we select the features based on some filter based method. So we filter off. We include some of the features or columns. Here features are nothing but columns. We include some of the features or we remove some of the features by using some filtration criteria. Then we have wrapper based methods, which are model driven methods. So basically when you are doing a filtering, when you are doing a feature selection, in that feature selection, we talk about filter based methods, which are primarily in the filtration, you are simply doing some kind of statistical approaches and you are just removing some of the columns. Whereas in the wrapper based methods, which will become more and more model driven, right? So we run some kind of models and based on that models, we'll talk about whether a particular feature is important. So we compute what is called as feature importance. And based on that, we will retain some features. We will knock out some of the features. So embedded are the ones which combine both these approaches, both filtration as well as the wrapper method. So we will talk through some of the examples. So that's the most important points that we are going to talk of in this session. So when we are using some of the things, I'll quickly run through. When we are using feature selection, we are also calling it as variable selection or attribute selection. So primarily what we are doing is we are selecting a subset of relevant features for use in the model construction. So out of the big list of features, sometimes some models, some data sets, you might have some hundreds of features. Not all 100 features will play an important role in predicting a variable, predicting the target variable. So how well do I understand all those features and knock out all those features will become very important activity. So especially if your number of features are too large, the feature selection will become a very, very important criteria. And at the same time, you can make your model more simpler. You focus only on some of those variables which are really impacting the prediction. And you would retain only those variables rather than keeping all the variables as such. Now that is where we can get our algorithms run faster because you are not using all the columns in the data. You are working only with a few subset of columns in the data. Complexity of the model will get reduced. Obviously, complexity is directly proportional to the number of features that are there, number of explanatory features or number of predicting features that are there in the data. So because of that, the accuracy of the model also can increase, especially because of overfitting. If more number of features are there, there is even a high possibility of overfitting. That too, irrelevant features. It's not about more number of irrelevant features are there in the data. It might very well lead to overfitting of the result, overfitting as well. So the model gets overfitted, and because of that also it might. So if you are using feature selection, it might reduce the overfitting. So basically you have to see that feature selection is mandatorily done before you start running your machine learning model. So these are some of the things that I want to take care of in that end-to-end case study. I'm just still testing out a few things so that all combinations can very well be fitted into that. So looking at the types of feature selection, we said there could be a univariate and multivariate. So univariate is the most important to start with, and multivariate is model driven, which is what is a wrapper kind of a method. In univariate, we are focusing more and more on filtering based method. Okay. So univariate always looks at the predictive power of the individual feature. How good? So can I really use this feature or should I knock out this feature? So it is the primarily in all the univariate mechanism, we are trying to look at the relationship between each of the predictor variables and the target variable. How strong is the relationship between the predictor variables and the target variable? So that is what we are going to look at. And based on that, so you will knock out some of the variables using this univariate. And after that, you will work on the multivariate. So some of the things we might have already done. Remove the features with low variance altogether. We have talked about those things earlier. So zero variance columns, better remove them directly because they don't add any value to the model. So because when you are collecting the data, you don't know whether there will be a variation in the column or there would be one single column, because the data collection phase many a times that much of care and this thing is typically not given. So any variable, any column which has only one unique value in that column, you should directly remove that column. Sometimes near zero variance columns are also worth deleting. What do I mean by near zero variance? Probably if I am talking about, let's say, 1,000 observations, right? 10 of them are having a V1 value, and the remaining 990 of them are having a value of V2. Let's say it's a binary variable. Obviously, these kind of things we have already taken care of. We have already taken care of, because anything that is less than 30 with respect to the categories, we have directly omitted them in the first step itself during our data cleaning process itself. But sometimes what could happen is, let's say we talk about 1 lakh records instead of 1,000, right? And probably 100 are from V1, and let's say 99,900 are from V2. Now, in that case, right now in our initial process, we are not deleting them. But in a large data set, probably this 100 may or may not be of significance. If I look at the probability of V1, it is 100 divided by 100,000. So which is like 1 by 1,000. So 0.001 is the probability of occurrence. Probability of not occurrence or probability of V2 occurrence is 0.999. So if I look at this binary, the variance of this data set is nothing but P into 1 minus P, because it's a binary data. It goes like a binomial distribution. So it goes with 0.001 times 0.999 So the variance of this data is nothing but overall it comes out as 0.000999. So it's as good as almost 0.001 approximately. Now you could see if this kind of a variance is also there. Let's say, so I can set that probably if the variance is around 0.001 or less, then also I can say remove that column. So normally 100 might be a decent size, but if I'm talking about 1 lakh observations where 99,900 of them are of one category and only 100 of them are of another category, sometimes the information that might very well come out might still be a kind of a biased information. So that's where what we said sometimes is, especially very low variances also, especially when the number of columns are too high in the data, you can even think of removing very low variance kind of columns as well. Zero variance, definitely you should remove it. But if it is not a zero variance, but it is a very low kind of a variance also, then also we should start removing that. All right. So that is one more point. So here, a feature with a zero variance means it has the same value for every sample, then such feature should be removed. Right? Sometimes the second thing we look at is correlation. So basically, if we are having, so now let's look at the target variable versus the feature explanatory feature variable. If the target variable is a numerical variable, then I can very well look at the correlation between the target variable and each of the feature variable. And if at all the correlation is insignificant, if at all the correlation is insignificant, you can directly drop, because we are talking about in an individual context. In a multivariate context, then probably you can talk about multicollinearity, lot of other dimensions. But in a simple univariate, there should be only if that variable is having some kind of relationship with the target, retain that. Otherwise, you can better knock it out. And probably another way of looking at it also is, you can knock it out even after doing the kind of transformation, adjusting it for normality. And both the dependent variable and both the target variable and your feature variable, both of them are almost close to normal. Then you can try the correlation. And if the correlation is still very insignificant, probably you can think of knocking out. Probably I'm just loading one data set, that same housing prices data set that we have worked earlier, because the dependent variable there or the target variable there was the sales price. So I have taken all the columns, right? I have taken all the columns, all the numerical columns, and for each of the column, try to find out what is the Pearson correlation coefficient. You could see here, probably will print. Okay. So we will see here. I have just rounded it up to 3 digits after the decimal. So I could see that almost all these columns, x of I is every column. So x is, if you see here, the x is except for the first column, except for the last column, which is your dependent variable. I am, except for that, all of them are typically being included as x. So all the columns are included as, so possibly we'll try to print that. Right, by now you should be comfortable with this notation. So take all the rows, take all the columns except the last column. So this is all the X. All these columns are included. Sales price is the last column, so that would not be included. Then what we are saying, you loop it. Take all the columns. So take the each column, each X column, each Y, so Y column. Take the Pearson correlation between the two and round up the values to the 3 digits after the decimal point. Okay. So based on that, I'm saying that every column, possibly here, so the correlation is there, and this is the p-value. P-value is coming out less than 0.05. So this variable will be a significant variable. All these variables will be significant variables individually, but this variable may not be a significant variable at all because the p-value is greater than 0.05. So 1, 2, 3, 4, 5, 6, 7, 8, ninth variable. So ninth variable probably may not be a useful variable directly. Right? Of course, I did not check for the normality and all, but even that exercise need to be checked. All these things we will do them in our what you say, in our case study. But I am telling you, the normality check also needs to be done. Otherwise, there could be a kind of a non-linear relationship that could be present between the two variables. So if you do a kind of a logarithmic transform or some kind of a non-linear arithmetic, non-linear algebraic transform on the data, and if the data comes more closer to normal, then you can very well try out both the data points being normal distributed. You can very well try out the Pearson correlation between them. Otherwise, you should start looking at a non-parametric correlation like the Spearman correlation or something. So we will look at those dimensions as well. Right, the ninth one, 1, 2, 3, 4, 5, 6, 7, 8, 9. So the basement fin SF2. It is looking like an insignificant variable because the p-value is greater than 0.05. And similarly, 10, then the fifth one after that. So 1, 2, 3, 4, 5. So basically, there is one more variable called low quality fin SF. So that one is also looking insignificant. Like that, you could see 3, 4, 5, 6. These 6 variables are coming out to be insignificant. So directly, if at all they are already normally distributed, we can very well think of knocking those variables out because they are not having any kind of a significant impact on the target variable. So these variables are not having, and even the last 2 variables for that matter. What are the last 2 variables? The year sold and the miscellaneous value. So you could see that those 2 are literally insignificant. So the year sold is typically not making any kind of an importance as such. So like that, you can very well knock out some of the variables also. That is one aspect of feature selection. Okay. Let me just please explain once. I don't know which one are you referring to. Right. Please be specific because I may not be looking at the questions immediately. So be a little bit clear on the question. If any of the features is categorical, then does this method work? See, basically, if it is categorical, you are converting it into a numerical by doing a one-hot encoding. So after you do the one-hot encoding, we may want to get into this numeric, get into this exercise. But there, rather than, now it all depends on, so there what you can very well do is you can do a kind of ANOVA analysis, right? And based on that ANOVA analysis, you can very well decide whether that feature can be retained or not. But most of the times what happens is, we would be doing this analysis, we would be doing this feature selection after getting into the one-hot encoding. By that time, the one-hot encoding process would have been over. So that categorical variable also by that time would have been converted into a numerical variable. So what we would primarily be seeing is which categories. So we will still use the correlation analysis there also. But there we would be simply seeing if the correlation is significant or not. Because between ones and zeros for that particular category, if I don't see too much of a difference with respect to the target variable, then obviously there is no point in you including that particular category. So it's as good as the default category itself. So that's how you can knock out some of the categories also. So there are two approaches, Sachin. One, if you want, there are two ways. One is you do the ANOVA analysis or you do the t-test kind of statistical test before itself, before doing the one-hot encoding. Then what could very well happen is, if at all there is no significance, if at all in the ANOVA that categorical variable is coming out to be completely insignificant, you can drop that whole categorical variable itself there itself. Before you progress towards data pre-processing and all. But on the other side, no, if you have not done that exercise before and you have progressed until the data pre-processing, then you would have already executed the one-hot encoding. Then you do the correlation itself, knock out some of the columns which are not statistically significant. So both of them can definitely work. Okay. If there is any further question, you post the follow-up question. If it is positive correlated and negative correlated, so both of them are important. Even if it is positive or negative, we don't mind. It is significant, right? Because sometimes possibly my sales will come down with some variable increasing. That is also an important variable. So it does not matter whether the correlation is positive or not. What matters is whether it is statistically significant or not. We have to check the correlation of a particular variable with every other before omitting. Okay, with every other is a secondary point. First thing, with the target. With the target, if it is irrelevant, it has no meaning to keep that. There is no meaning to keep that, right? Because it for me, target is, so many a time, the point that you are referring to, Nayan, is it is having a very good correlation with the dependent variable, with the target variable, but it may also be having correlations with other variables as well. And because of that, it could create a kind of a multi-collinearity effect. So there, possibly before removing, we are looking at all these things. But when we are directly seeing that the correlation itself is not existing, so what you are referring to is a slightly different case. You are bringing the opposite case. You are bringing a scenario where we are running a linear regression model and one variable has come out as something insignificant, then probably before dropping that variable, I may have to look at the importance with the other variable. But here I am doing a one-to-one pairing analysis. So in this analysis, if I am really getting an insignificant variable, provided both the variables are normally distributed, because that is where the linear relationship between the two variables can be tested more appropriately. So in that, so the non-linear relationship we can try to avoid in that case. Code 21. What is the code 21? Okay, 22. Possibly this is the one you are referring to, 21, because it looks like I have run it here. Okay, so what is that we are saying? We are taking every column. So this is the data. In that data, except the last column, every other column I am taking as X. The last column I am taking as Y. For every column, so I am looping across all the columns of X, right? So I am finding out the Pearson correlation between the two. I am finding out the Pearson correlation with respect to Y. Y is my target variable. Any follow-up question from anyone else? So we would typically end up deleting these 5-6 columns. We can directly we can try to initiate, and we can try to delete this 5-6 columns. Sometimes we can even put some kind of a logic in terms of whichever are the ones whose p-value is greater than 0.05. X of I is nothing but it's a loop, right? So X is all the list of columns. X dot columns is the list of columns. So possibly when I'm talking about X of I, so the X dot columns, so are possibly you can, so if you really print your X dot columns, it's a list of all the columns. So I am taking I is in X dot column. So first value of I will be lot frontage. So I am taking X of lot frontage, which means that lot frontage column and the Y column. I am trying to find the correlation between the two. Why there is two value? One is correlation. The second one is the p value for the same. So this is the correlation and this is the p-value. The t-test is performed to identify the statistical significance of the correlation. So if the statistical significance, the second one is the p-value identifying the statistical significance. So if the p-value is less than 0.05, we say that this correlation is a statistically significant correlation, so I cannot remove it. But if the p-value is greater than 0.05, I can say that the correlation is not statistically significant, and probably I can think of removing it. So that is where I am saying this particular correlation is not statistically significant, so I can remove. This correlation, this particular variable is not having a significant correlation, I can remove, and so on. Does that answer your question? Okay. So which means you could clearly see if the correlation amounts are very, very small, we see that the p-values will be much larger. So basically when the correlation amounts are much smaller, the p-values will be much larger. So they are worth removing. Now, even if this correlation is 0.099, the p-value is still looking like 0 point, which is 0. So this correlation could be very small, but it is very significant. But it is statistically significant. So wherever it is statistically significant, we can retain it. Only when it is insignificant as given by the p-value, then we can drop it. Okay, so the Pearson correlation could be a positive, negative, or zero. We have talked about it. So if the value is close to zero, it's a weak correlation. Close to 1, strong positive correlation. Close to -1, strong negative. Let me see which ones are having such a kind of huge. So you could see this one, strong positive correlation, almost 0.78, 0.7, almost close to 0.8. So which is that variable? The third variable. So overall quality is very positively correlated with the price. Then which one else? Possibly this one is also decently positively correlated. Right. I don't see anything that is highly negatively correlated. Right. Some of them are positively correlated highly, and some of them are moderately positively correlated. But definitely there are few negative correlated, but very mildly negatively correlated. Significant, but very mild, because they are very much around zero only. So this negative is uncorrelated, this negative is also uncorrelated, this one is also. So majority of the negatives are looking like insignificant, but only 1 or 2 negatives are looking slightly significant, but they are negative. Okay. So there are a few things regarding the correlation. Just wanted to say, if at all the two correlations are highly correlated, X and Y and Y and Z, I can't directly, oh sorry, this is X and Z. So X and Y is highly correlated, Y and Z is also positively correlated. I can't say that the correlation between X and Y will be very strongly positive. Right? Not necessary. Right? So that's one thing, because generally what we say is, if let's say I'm talking about the correlation between X comma Y is some 0.8, correlation between Y comma Z is 0.7. Right? Probably if I want to look at the correlation between X and Z, it actually has some kind of a range. So probably I can take it as 0.8 times 0.7 minus square root of 1 minus 0.8 times 1 minus 0.7. So somewhere I can very well have some such kind of a relationship. So it can be even to this extent as well. 0.56 minus square root of 0.06. So it might very well lie in that kind of a range as well. So that could be a kind of a minimum value that can be associated with this kind of a correlation. So because of that, what we can say is it's not a kind of a transitive relation. Right? The moment I'm saying this correlation is high and this correlation is high, not necessary that the third one, X comma Z, also will be higher. I'm only trying to say that. Right? Not necessary. That is what we are simply calling as the transitivity principle. That's one important point associated with correlation. Correlation is very much sensitive to outlier. That's the reason I was talking about. You try to do a kind of a non-linear transformation, try to get the data more closer to normal, and after that try to check on the correlation, where you will find to a large extent the better relationship between the observation. And it does not capture the non-linear. So if at all you are seeing, when you are doing a scatter plot or something, if you are seeing that a particular variable is expected to showcase some kind of a non-linear relationship with respect to the target, better don't remove that feature. but better try looking at doing some kind of a non-linear transformation on that polynomial transform or something on that data, and then try to fit the model, right? So when it comes to the practitioner's perspective, what all we can do with respect to feature selection. So there are two major things that we want to focus on with respect to feature selection. One is how many selection criteria, how many you want to select. So let's say if I have 100 features, how many of those features you want to select? Is it 10? Is it 20? Is it 20%? Is it 50%? So either it could be in terms of percentage or it could be in terms of actual number. So that is where we have the functions that talk about select k best or select percentile. So you can very well use either of these functions. So that is the selection criteria. How many you want to select? You want to select, so we'll use them, but how many you want to select? It could be in terms of the actual number or it could be in terms of the percentile. Now, what is the kind of criteria, right? What is the kind of a metric you are using for that? So you want to select the 10 best features. Now, what is the metric you are using? So one metric is correlation. We have already used that correlation, and based on that correlation, there you are only saying significant and insignificant knockout. But within the significant also, if there are, let's say, 60 features that are significant, but I want only 20 features, top 20 features, then I should give a kind of a criteria measure. So one criteria is, let's say, I can use an F test, right? In case of regression, I can, this is purely coming out as a kind of a linear dependency between the two variables itself. I can use an F test, I can use a T test on the top of the correlation, or I can use something called mutual info. This is something which is a non-parametric test. Mutual info based test is a non-parametric test. So it does not bother much about whether the data is normally distributed or not. Sometimes you may prefer mutual info if you are not looking at normality, adjusting your data for normality, doing some non-linear transformations, algebraic transformations on the data and all. But if you still want to do some kind of feature selection, then you can go for a mutual info based feature selection. Mutual info based feature selection, it typically uses a non-parametric kind of an approach. Probably we can Google it out, but what it simply does is it takes the probability or joint probability of X and Y, divides it by the probability of X in typical and probability of Y, takes the logarithm of this, and it multiplies by the joint probability of X and Y. Now, this is in case of a discrete, whereas in case of continuous, the same thing would get translated into a kind of an integration kind of a format. So the joint probabilities of X and Y divided. So basically what would happen, there would be a kind of a discretization of, if you want to look at it in a real world scenario, there would be a kind of a discretization of continuous data. And based on that, this kind of summation or integration across all the possible values are typically taken up. And based on that, you would find out the mutual info value. And based on that, if I see that the mutual info value is significant, that variable would be retained. Otherwise, that variable could be very well knocked out. Yeah. What is F regression? It is nothing but you are doing an F test, right? F test. F test is a kind of a statistical test. So you are running a kind of a regression with that particular variable. You are looking at what is the statistical significance of that variable. So it is in a way very much related to your correlation based t-test itself, right? If you remember, you run any kind of a linear regression, even with a single variable, you will get an F value, not through the machine learning mechanism, but through the typical statistical mechanism. If you run a linear regression, then you will get the F test and the P value corresponding to that F test. So what we say is if that P value is less than 0.05, in a single variable mechanism, your F test and T tests are very much highly correlated. So we have a function for F test regression here, but what we are doing internally is nothing but a correlation based variable selection itself. Okay. So like that, even in case of classification, you can use a chi-square test also. If the variable is if both the variables are categorical, you can think of using a chi-square test, or you can very well use an F test there also for a classification model. And you can use a mutual information based. Mutual information is always based on the mutual information theory, which is a non-parametric kind of a mechanism. So even a continuous data will be converted into discretization. It would be converted into a categorical data. And based on that, the joint probability of occurrence of X and Y divided by the individual probabilities of occurrence of X multiplied by the probability of occurrence of Y, a logarithm of that, and you multiply it with the probability of joint probability of X and Y. But all these we have functions. So when we have functions in the practitioner's world, probably all we need to know is that this is mostly a kind of a non-parametric kind of an approach, and based on that mutual information, I should be able to take a call. So that's where I have integrated all these things into the case study, so that practically we can see each of these things, and based on that we can take a call. So filter methods are generally used as a pre-processing. Before you start running any kind of machine learning model, where the filtration is very important, because you want to knock out some of the irrelevant variables altogether. Right? So we will look at the scores by using different kinds of criteria. Right? So we should have a metric to evaluate. So based on this particular metric, based on the F regression score, based on the mutual info based regression score, based on the chi-square test related score, I will select 10 best variables, or I will select 20% of the total variable. Now this is what is a typical feature selection mechanism using the filter method. Right? So we will look at statistical scores, various statistical tests, and we look at the scores. And based on that, we will retain or we will knock out that specific variable. So if you really look at the correlation base, I have taken the correlation for all the variables. So we got the correlation. We could very well see which of them are least. So we have already seen some of them are least, having a least correlation with respect to the dependent variable. So wherever you are getting the least correlation with respect to the dependent variable, you can knock off those variables. Or let's say you look at this one, we are going with a mutual info regression. Mutual info regression, as we have said, it is based on a non-parametric kind of an approach. So what is that? You just see here. I am taking the correlations right, with respect to the sales price. I am trying the correlation. I am trying to take the correlation for every observation with respect to the sales price, right? So I am sorting it based on the correlation. I am doing a sort on the ascending order based on the correlations, and I am printing that. So you could see here, the kitchen above greater is having a minus 13, minus 0.13 kind of a correlation. Enclosed Porsche is having a minus 0.12 correlation, and so on. Whereas on the other side, I see a overall quality having a very high positive correlation of 0.78. Greater living area is having a positive correlation of 0.70. Now, I can very well say I want to retain only those correlations which are the absolute value is greater than 0.2 or 0.1. I will retain only those correlations. So here I am not doing, this is not the mutual info. I am going with a correlation based feature selection. So all I am saying is for everything I am doing the correlation. And probably what we have done earlier is I have also looked at the p-value, right? So possibly I can say here you could see that the correlations are 0.02, 0.00, which are very, very low. So sometimes only here 6 are getting removed, right? So what I can very well say, the other way of doing it is, I can specify what should be the cutoff correlation, right? So I have computed the correlation for all the variables. And once I have computed the correlation for all the variables, I am now taking a call that retain only those variables which are having a correlation of at least 0.2, whether it is positive or negative. So in that case, it looks like only these are the columns that are having more than 0.2 correlation. So I might very well say retain only these columns. Only retain these columns, remove all the other columns. So suddenly you are getting into a kind of a reduced set of data altogether. Okay, let me just see here. I think lambda is something that we have discussed in our initial classes, Kondababu. I do remember we discussed about. So possibly it is like it will avoid. So this is one of the Python features we discussed in our initial classes. So it's like you write a function normally and you call that function. So possibly I'll write like this. I'll say define. We write a square of x. We write some function, right? And say return x squared, right? And probably I will call this function as square of 4. So so which means it will return 4 square, which is 60. This is like you are defining a function separately and then calling the function. Whereas in lambda, you can simply say without defining the function dynamically lambda x colon x square. So whatever is your value of x, the x squared will be computed. So that's where probably you can on the fly you are defining your function. So for every x you return x squared. So you can very well say you can very well pass your values and you can get the squares directly. So you don't need to define the function separately when you are using the lambda. So here if you see, what did I do? So I am taking, so I am applying the lambda for x, right? X dot correlation with respect to the sale price. So X is whatever the column that I am taking. So the entire data column. Data is having so many columns. So in each column, you apply correlation with the sales price column. So every column, you will apply the correlation with respect to the sales price column. In one single line, we are able to execute that using the lambda. And once I am sorting, now someone is asking what is arg sort. So arg sort is basically you are trying to put a kind of a sorting in the array. So along with the indices. So along with the sorting will happen along with the indices value. And you are catching hold of the indices. So you are important based on the importance, you are sorting and you are also capturing the indices associated with them. And probably the same thing is typically being printed. Yeah, lambda, I think Paras has already explained. Lambda is a very good feature in Python, can be used for any anonymous function. You can very well create, you don't need to define the function. But of course, it has its own limitations, very difficult in some complex functions. For complex functions, you should very well write the function itself. But typically, if you are having a simplified kind of one-liner kind of a function, you can write it within a kind of a one-line scenario. Then you should definitely use the lambda function. Okay, please help me to learn the concept of fit transform, column transform in scikit-learn. Okay, so anyhow, we are going to use it. Fit is you are just fitting the model, right? It's a very simple. You are just fitting the model. So normally what happens? Okay, so when you are fitting something, it's like it's a generalization that is happening. It's not applied to the data. But when you are doing a fit transform, there is a generalization that is happening because of the fitting. And that fitting is applied to the given data also. And the data is also transformed. Right? So scikit-learn goes with whether you just want to generalize it and you want to fit it on some other data, or you want to generalize it on the same data and you want to fit it to the same data also, then we are using fit transform. Okay. I think, I don't know, column transfer, I did not get what exactly you meant. But fit transform are the two most common things that we keep using. I think we will also use in our case study. So you will get much more clarity on that as well. Under pre-processing, but I'm not wrong. Yeah, pre-processing wise, so basically that non-linear transform that I do, right? Or probably you want to do a scaling, like Z score transformation or min-max kind of a scaling. We discussed about them. Or absolute scaling, right? Max absolute scaling. So if you want to do some such kind of a scaling, or if you want to do some kind of a non-linear transformation like a power transform, or if you want to fit something like one hot encoding. In all these cases, there is a fitment. Fitment will only do the capturing of the generalization. So the model can be built by using fit. But by using fit transform, the model is built and that model is tested on the on the data itself. So that way, two steps are happening in one single shot when you are going with a fit transform. I hope that is clear. Otherwise, please put one more follow-up question. Okay, so here we got the correlations listed, and probably there are so many, right? So what I want to say is, I don't want all the correlation. I want only those where the correlation is greater than 0.2. The absolute value of the correlation is greater than 0.2. So only these are there. Then I can put some kind of a subsetting. I mean, we can do some of those things in terms of shortlisting, that these variables are sufficient. All other features, please knock out. So that is when I'm using the correlation as a mechanism. Then the next mechanism, I can also use the mutual info. Mutual info, as I have already said, it will do some kind of a non-parametric kind of an approach. So if you see here, I'm trying to look at the mutual info regression between X and Y, right? So probably we'll go step by step. So if I take the mutual info regression between X and Y, it calculates the mutual info score between your target variable and the each of the independent variables that you had. So it will compute the mutual info score. And as I told you, the mutual info score is typically computed by this kind of a mechanism. Right? The mutual info score is computed by this kind of a mechanism. So for just like correlation, but correlation requires lot of normality of the data, linear relationship, all these things. In case of mutual info score, we are not at all looking at the distribution of the data, because this is a kind of a non-parametric test. And in this mutual info regression, mutual info score, we are looking at the score between the dependent variable and the independent variable. So I am now converting this entire NP array. So because we are getting this mutual info score is coming out as a NumPy array. So I'm converting that NumPy array into a series, because I want to assign some column names to that, because NumPy does not take any column names or anything. NumPy is completely for numerical data. So if I want to put some kind of column names and probably a print, then it is better that NumPy arrays are always converted into pandas series objects. Then once I got that, I have given the column names to all of them through the index. I have sorted those values in the descending order, and I am also plotting them. I am putting a kind of a bar chart on them. So now you could see the mutual info score. Now correlation actually lies between -1 to +1. But mutual info score lies between 0 to 1. It does not have a negative value. It only lies between 0 to 1, because they are all probabilities. Right? You could see that they are all probabilities. So what we could typically see is, this mutual info score, the higher it is, the better it is. Higher it is, the better would that variable be. But if it is very close to 0, then it means that that variable is an irrelevant variable for our model. So you could clearly see here, I'm sorting all of them. Probably you could see the overall quality, even through this mechanism also, it looks like the overall quality is having the highest MI score. You could see in the correlation also, we got overall quality as the highest correlation score of 0.78. Even in case of mutual info, it is the one that is coming out as the most important variable. Followed by GR living area, total basement square feet. Let me see there. GR living area is still the second, but total basement square feet here is at the probably fifth place or something. But in the mutual info, it has come to the third place. What happened to the garage cars and garage area? Let me just see. Yeah, garage area is also slightly better off garage car, but slightly the orders have changed. The year built, actually here, somehow the year built came out to be a very important variable. Using the mutual info, it looked like the year built has come out as a one important variable. Okay, here also it came out. Year built, it has come out as an important variable itself with a 0.5 correlation. I think year sold was unimportant, right? Probably year sold, the correlation was very less, but year built, here also it is having a decent correlation, and even in the mutual. But you could see here, the last few variables, they are having a very low value of mutual info. So again, here also you can put some kind of a cutoff. Let's say 0.05 or 0.02. So any of those variables which are having a less than 0.05 in terms of mutual info score, I can knock out those variables. So like that, we can very well simplify the problem as well. Right? These are all for simplifying the problem. All right. So either I can use a mutual info base, or I can use an F-test based or kind of correlation based, or in some cases, if it is a categorical variable, if my target variable is a categorical variable, then I can also look at a chi-square base as well. So all these things, I thought I will take them up in the case study that I am going to take up from tomorrow. So that is the reason I'm just giving you an intro to all these things, but we'll try to take up each one and try to put them into our case study. Now, as I have highlighted, the filter methods, they do not remove multi-collinearity because we are only looking at one variable at a time. So the joint relationship between multiple variables, those kind of dimensions are not looked at in the filter method. So basically, we are only removing those variables which do not contribute anything as an individual. So they contribute nothing as individual. So basically, you can remove them from the model. Right? So one must, so which means just by doing a univariate approach will not solve or will not remove all my irrelevant variables. I should also go with the next steps, which is the multivariate kind of feature selection also, to ensure that the final list of variables that I am using for building my model, they are really the best contributing kind of list. That is where we get into the wrapper methods. Wrapper methods, they are purely model driven. Right? Basically, the filter methods, they are all statistical. I don't need to run any model for a filter method. Right? I don't need to run a model or something, which means they are very fast to execute. I don't need to run any model. I don't need, so they are not model dependent. So they are easy formula driven kind of thing. So filter methods are faster to execute, but obviously they have a limitation that they don't handle multicollinearity, etc. But at the same time, they cannot be replaced. So you need to have feature methods, filter methods, and on the top of that, you need to look at the wrapper methods. So we try to use a subset of features and train a model. And based on that, we will either retain the variables or we may drop some of the features. So typically, we can say two methods. One is a forward feature selection, backward feature elimination, or recursive feature elimination. So it's as good as like this. So if you are having, it goes like this, forward approach. And the second one is like a backward or recursive. So it goes like this. So let's say we have 30 features altogether, right? After removing all the, based on the univariate approach, let's say you have removed 10 from 40 and you are still left with 30 features. Now what will happen is, initially, 0 features are included in the model. No feature is included in the model. Now, without including any feature in the model, I will compute what is the error of the model. What is the error of the model without including any feature. Now, individually, feature 1, only one feature at a time. Either feature 1, feature 2, feature 30. Or each one of them will be added only one at a time. Out of all this, what is the error? So if feature 1 is added, only feature 1 is added, what is the error? Only feature 2 is added, what is the error? Only feature 30 is added, what is the error? So which one out of all these has the lowest error? Let's say by adding feature 2, the error became the lowest. Then in the first iteration, feature 2 will be shortlisted. Then to the feature 2, the other features will be tried. Feature 2 plus feature 1, or feature 2 plus feature 3, feature 2 plus feature 4, feature 2 plus feature 30. Now in this case, which of these combinations is having even further lower error? Which of these combinations is reducing the error even more further? Let's say if this combination is reducing the error a lot, then now your list will contain F2 and F4. Now in the third case, now again F2 plus F4 plus F1, F2 plus F4 plus F3, and again the same process will continue. So as long as the error is further getting reduced, right, by adding one more variable, as long as the error is further getting reduced, I will keep adding that extra variable. But let's say after adding some 12 or 15 variables, if I am adding the 16th variable to these 15 variables, the remaining, all the 15, any of the 15 variables, none of them is able to reduce the error further. If none of the remaining 15 variables, they are able to reduce the error further, then what we say is it is saturated and only 15 variables will be included into the model. The remaining 15 variables will be knocked out. So that is what is the concept of forward selection. So you start with 0 features and after that you keep adding feature by feature depending on to what extent that extra feature is adding value to the model and reducing the error of prediction. So that is what we typically call as the forward selection mechanism. Then we are talking about the backward or a recursive selection kind of a mechanism, where you start with all 30 features. You start with all 30 features, find the error. Then start removing one feature at a time. Remove F1. See what is the, so whether the error has increased or not. If the error has increased by removing F1, probably F1 cannot be removed. Similarly, remove F2, F30. So in which case, the error did not change much. Error did not change much. So that one, let's say with F21, the error did not change. In the original, when I included all 30, let's say the error is 100, right? And when I removed F21, the error became, let's say, 100.1. So which means the error increased, but this error increase was very, very marginal. Whereas if I removed F1, suddenly, let's say the error has gone to 120. By removing F1, let's say the error of the model has gone to 120. In that case, F1 should not be removed. Probably F21 can be removed because the error did not change much at all. Now, this is where, or probably when I removed this F21, let's say the error became 99.9. Right? So it has actually reduced by removing F1 rather than keeping F1. By removing F1, the error has got reduced, or probably let's say it became 95 only. Better knock this F21 out already, because the moment you have removed this F21 from the model, your error has actually come down. So which means that that particular variable, there is no point in including into the model. So this process is what is like a backward elimination. You start with all the features and you knock one by one out till you get the least possible error. So yes, backward and recursive is just the opposite to the forward. Okay, so these are the two different feature selection wrapper based methods. So you can talk about forward feature selection is an iterative method in which we start with having no feature in the model. In each iteration, we keep adding the feature which best improves our model till the addition of a new variable does not improve the performance of the model. Similarly, backward feature elimination, we start with all the features and remove the least significant feature at each iteration, which improves the performance. So if I am removing, after removal, the performance should be better. So if I am talking about the performance in terms of error, the error should be the lower. We repeat until no improvement is observed on the removal of the features. So this is also called as recursive feature elimination. So this is also one way. This can take care of multi-collinearity present in the data as well. So it will always look out for the best performing feature subset. It repeatedly creates models and keeps aside the best or the worst performing feature at each iteration. Okay. So it constructs the next model with the left features until all the features are exhausted. So it will remove one by one, and until I don't get any kind of a further removal, further benefit on removal. In this too, which is more preferable? It all depends on how many variables are there. So if you just want to include 10 variables or something, then and if you have 100 variables altogether in the data, then probably the forward selection is much better. Whereas if you are fine with including excluding only 10 variables, then and want to include 90, then instead of forward selection, the backward elimination or the recursive elimination is much. So if there are too many features that are already present in your data, better work on the recursive, right? I mean, if there are too many features in your data, better to go with the backward or a recursive. But if there are only few features altogether in the data, then you can very well look at a forward selection kind of a mechanism. So mostly we go with the recursive feature elimination itself. Now you see this, a small example, but in the case study, we will definitely use it. Now this is how I'll use it. So I'm using recursive feature elimination process. I'm using a linear regression. So these are all model driven. So here I am using a linear regression, but I can very well use a random forest or some other kind of a machine learning model as well. So I build. So what is that we are saying? You initiate the model. You take your X and Y. X is typically, it does not include the last column. Y is the one that includes the last column, right? So now we are doing a recursive feature elimination by using this linear regression model. But now this model can be substituted with any other model as well. And we are saying you only select 10 features. By using the recursive feature elimination mechanism, you select only 10 features. Now, again, I'm now referring to the fit and fit transform. Now, this is just generalized. So I'm just fitting between X and Y. So I don't need to apply this on the data. I want a generalization. So I'm simply fitting it. So by doing the fit for this recursive feature elimination, I'm fitting between X and Y. Now I'm storing it in RFC. Now I want to know what is the support, which of them are included, which of them are excluded. Right? This is a model that this is a generalization that happened. On that generalization, I am trying to look at which of them are included and which of them are excluded. And I'm also looking at the ranking of each of them. Because if I really want to include a few more, then ranking could very well help. Now I could clearly see that this one, the third variable is getting a true. The fourth is getting a true. Now what are those, each one of them? Probably we'll go with X dot columns. Sorry, columns is not a function. So the first and second are omitted. Probably the third one is good to include, overall quality. Fourth one is also good to include, which is the overall condition. Probably after that, all are getting knocked out, right? And these are getting included 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 16, 17, 18. 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. 16 is basement full bath, basement half bath, full bath. So these are some of the variables that are getting included. Bedroom above, so something. So these are some of the variables that are getting included, whereas many other variables are simply getting knocked out, right? All these variables are typically getting knocked out. So you could see that the ranking wise, all those that are included, they have got a rank of 1. So these 5 and 5. So these are the 10 that have got a rank of 1. Right, we have got with 10, but I think it has given 11 altogether. No, 10 only. So there are 2 here. 2, 3, 5, 4, 9, and 1, 10. So these are the 10 that got these are the 10 that got the rank of 1, and after that the rank 2. So rank 2 is this one. So this is my next important variable going by the recursive feature elimination. RFE.support is nothing but, so we have already said in RFE, you select only 10 features. So support is simply saying which are the 10 out of that 34. So which of them would be included, which would be true, which would be excluded, that would be false. It is only given whether that variable is selected or not. That's true. Right? Because we are explicitly saying that you select 10 features. It is saying, we are saying select 10 features by using the recursive feature elimination mechanism. So based on that, it is shortlisting which one is selected, which one is rejected. So I can use this way, either forward selection or a recursive feature elimination. To a large extent, it would always be a better to go with the recursive feature elimination mechanism itself. Then you can very well go with the embedded. You can do both feature selection as well as a wrapper method. Right? If you see lasso, if you remember the lasso that we have discussed earlier, lasso will by itself put some of the coefficients to 0, because in the minimization function that we discussed, along with the squared error minimization, you also talk about absolute value of the coefficients to also be minimized. So in that process, it can very well happen that some of the coefficients will be automatically made to 0. In the lasso. In the ridge, they will not be made to 0, but their value will go very low, that they can virtually be considered as 0. So that way what happens is, internally, they are explicitly, these algorithms, they are wrapper-based algorithms itself, but at the same time, they are directly removing the importance of the variables, just like a feature selection, just like a filter method. So that is where you can very well say that when you are using lasso and ridge in your models, it is as good as you have embedded the filter as well as the wrapper methods into your selection mechanism. So just like the way I used a linear regression, now you can also use a decision tree, right? You can also use a decision tree. Let me see if that directly works or not. If I'm doing a decision tree based regression, I think I have to from sklearn.tree. From sklearn.tree, import decision tree regressor or regressor. Okay. So now let me see. You see, it is giving a different mechanism. The model is changed. Now I have changed using a decision tree regressor. I could see using the decision tree, the order is different now. right? You could see here earlier the overall condition was included, but using the decision tree, lot area is getting included, right? And so you could see there could be a change. Probably the fifth one is included, which is like a year built is getting included into the model, right? So which means depending on the algorithm, so these are like a model dependent, right? So depending on the model that you are using, your variables would be either included or excluded. So you can use the other tree-based mechanisms like random forest, gradient boosting. So when we are discussing about them, we can very well get more clarity on that. So basically, if you look at the filter versus the wrapper, filter methods measure the relevance of the features by their correlation with the dependent variable. To a large extent, 1-to-1. The target variable and each of your feature variable. So it's only one at a time, right? Correlation with respect to the target variable. Whereas the wrapper methods measure the usefulness of a subset of features by actually training. So they look at it as a total, whereas the filter-based methods, they evaluate on an independent basis. Filter methods are much faster compared to the wrapper methods as they do not involve training the model. It's only a simple statistical test. So that way you can simply eliminate the variables much faster in filter. Whereas wrapper methods are computationally very expensive, right? But definitely they identify the multi-collinearity in the variables and they give a better solution. Filter methods use statistical methods for evaluation of a subset of features, while wrapper methods use cross-validation. We talked about the cross-validation earlier, right? So any model-driven will internally use a cross-validation, which is one of the ways of enhancing the reliability of the model. Filter methods might fail to find the best subset of features because they don't look at it in totality. They look at each variable in isolation. Wrapper methods can always provide the best subset because they look at the overall quality of the data rather than looking at one variable and its importance with respect to the target. Using the subset of features from the wrapper methods make the model more prone to overfitting because you can very well, when you are going for model based kind of things, right, it becomes more and more model driven. So some models, they can very well encourage overfitting, like a decision tree kind of model. They are more and more susceptible to overfitting as well, unless you bring in some kind of a pruning mechanisms. When we talk about those decision trees and all, we will discuss these things in much more detail. Now, so basically, this is talking about if I'm using a decision tree mechanism, how do I really look at the feature selection? So let's not get into this because this I will put it as a part of our case study. So I'm using the random forest, and based on that, again getting the scores. This is all same. Whatever is the method that you are using, you are getting the scores, and based on those scores, you are sorting on those scores, and based on that sorted scores, you are selecting which features to be included and which features to be excluded. So this is the feature that has got the best possible rank, and these are the features which have got the least possible rank. So basically you can knock out some of those features if they are not making any sense. The same thing we are plotting in a bar chart, right? These are just simple things. So basically the most important takeaway from here is I have to think which features to be included and which features to be knocked out before I actually jump into any kind of a machine learning model building exercise. So this is one more pre-processing task. So what we are saying is probably all these are the basic minimal things that we need to be comfortable with before you move forward building any kind of a model. So with these things, I think we are very much in a position to go ahead working on the data end to end and start building our model. So we will use that same loan data set that we have used earlier, but I will try to take a minuscule version of that data set because that data set actually contains 1.5 lakh rows. So some models may take hours and hours to execute. So from that perspective, I would try to restrict myself to a small data set of some 2000 or 5000 kind of records out of that 1 lakh, so that we can look at multiple models within a small span of time. So that is what I think from the next session, we may take another 3 or 4 sessions exclusively or more than that to exclusively do that case study on classification. In fact, I started building that. I'm testing it out with a few aspects. I tried to build a lot of these models already. Some of them are already executed. So from tomorrow onwards, we can get started with the discussion of this. So it contains the entire process, right from cleaning of the data and all those things. So possibly we can take it like a real-time case study and then see why not this step, why this step kind of discussions as well. All right. So if you have any questions, I would like to take them up now. Otherwise, I think we'll end this session here for today. I will share this sheet as well.